Last time, we discussed how a series RLC circuit behaves when subjected to a sinusoidal voltage source. Now let us look at the behavior of these components when connected in parallel. When an ideal inductor and capacitor are connected in parallel to each other, they behave as follows. First, the impedance of this setup can be calculated using the parallel resistor formula, and it simplifies to this formula. When the driver frequency is low, capacitive impedance is large and inductive impedance is small, so the circuit impedance is capacitive. Generally, when impedances or resistances are connected in parallel, the effective impedance is lower than all the individual resistances in that network. Since inductive reactance is small at low frequencies, the effective impedance is also very small due to the parallel connection of the components and approaches zero as the frequency approaches zero. If the frequency increases, inductive reactance increases, while capacitive reactance decreases. This results in an increasing overall impedance, since this difference is getting smaller. So, from Ohm's law, the current decreases as the frequency increases. At a particular frequency, the two reactances become equal. This implies that their difference becomes zero, and thus the impedance of the circuit becomes infinitely large. The current through the circuit at this frequency is zero because the source can't drive a current through the infinitely large impedance. So, what is the physical meaning of the fact that the impedance at resonance is infinitely large? Well, it tells us that the capacitor and inductor are exchanging energy back and forth without external input. Here's what happens. The capacitor discharges, sending current through the inductor. As the inductor builds up a magnetic field, it stores energy. Once the capacitor is fully discharged, the inductor releases its stored magnetic energy, recharging the capacitor with reversed polarity. This cycle repeats indefinitely, with energy oscillating between the capacitor's electric field and the inductor's magnetic field. So, the circulating energy remains contained within the LC loop. This results in a condition called resonance, where the circuit naturally oscillates at a particular frequency determined by the values of the inductor and capacitor. The resonant frequency corresponds to the frequency at which the two reactances are equal in magnitude and is given by this formula. When the driving frequency is increased beyond this frequency, the inductive reactance becomes larger than the capacitive reactance, and the difference between them starts to increase once more. This means that the impedance, which is now inductive, starts to decrease and approaches zero as the frequency goes to infinity. So, current through the circuit begins to rise once more as you move away from the resonance frequency. In practice, there are energy losses due to resistances in the inductor and leakages in the capacitor. The major contributor of this resistance is the inductor, so in practice, the circuit is better represented as shown here. This changes the behavior of the circuit. First, the impedance now reaches a maximum finite value at resonance, while current reaches its minimum non-zero value. This no longer happens at the frequency where inductive impedance cancels out with capacitive impedance. One way to find the point where current reaches a true minimum is by varying the inductance and measuring the current through the circuit until a true minimum value is reached. At this point, the impedance will be at its maximum value. This point is called the anti-resonant point. Because of the altering of the inductance, the current is not truly in phase with the supply voltage, but as long as the unloaded quality factor of the circuit is high enough, the phase difference is negligible. Like with the series RLC circuit, the rise and fall of the current depends on the quality factor of the circuit. The curve is sharp if the quality factor is high and broad if it's low. The bandwidth of the resonance circuit is calculated using the same formula as before. A high bandwidth implies a broad resonance curve, while low bandwidth implies a sharp curve. That's it for this video. Thank you for watching.